Recently on the archive. Who's the apprentice? What? Who's the apprentice? Who's the one? Let them figure it out.
Q&A session officially begins. Yes.
So if I understand correctly, then classically in number theory, most of the difficulties with Eisenstein series are of analytic nature, and here I don't understand why the difficulties we had are of analytic nature. I feel like they were more like computing Whittaker coefficients of Eisenstein series, which in number theory was easy, right? So I'm confused about this.
Great. Okay, for me, I would say there's two things. So the first thing is there's a general feeling in the subject that the parallel to analytic difficulties and harmonic analysis is kind of homological algebra difficulties. So for example, like then it's formulated this assertion, and this assertion would not have been, and this is sort of like the Eisenstein particle theory, but this assertion wasn't something you could formulate until you really knew what input null was. So this assertion, there's no subtleties around, but this assertion, you really kind of have to be, so to say, careful about your functional analysis, which here means really which category you define. And so there's something that's happening here of like, well, for practitioners, that feels like the kind of analytic difficulties in some that feels parallel to the analytic difficulties that you see in the classical theory of automorphic forms. That's thing one. Let me try to answer thing two. So Dennis drew two commutative cubes, which he then really erased. And so the first commutative cube, okay, let me just call them squares. I'll ignore 5 in the faces. So the first commutative square was about computing what the Langlands functor does to Eisenstein series, which is about computing Whittaker coefficients of Eisenstein series. And so that was supposed to be understood as the easier of the two faces. The second thing was about understanding how the Langlands functor interacts with constant terms. And again, here you really kind of, when you formulate that statement, it'll be wrong if you don't do your functional analysis set up correctly. And in addition, what does it really mean? So kind of like Dennis explained that if you believe him that all of these various diagrams commute, then you kind of can quickly compute like that these two categories are the same, at least like modulo Langlands, let's say for a torus. For PGL2, you can quickly compute that these two categories are the same. And what does that really amount to? You take two Eisenstein objects, maybe they're both I shriek of something, and you try to compute their Hams and compare the answer to what you get down here. So their Hams compute a constant term of an Eisenstein series. Constant terms of Eisenstein series are also well understood in the classical theory of automorphic forms, but you see some kind of like Weyl group occurring in the formula. Yeah, that Weyl group it comes from some Bruhat stratification, and in like somehow in number theory, those strata you can deal with them one at a time, but in geometry they mix together. So you get sort of a filtration by the Weyl group where
They're glued together.
They're glued.
Not mixed there.
There's a filtration. There's a filtration where the associated graded terms are given by this Weyl group, but the sort of the X in the filtration extension classes are like subtle, and so it becomes hard to just sort of mimic that proof, and you run into like sort of a range of difficulties. It's very, very closely related to sort of the local theory Dennis was talking about here. So the local theory here is kind of meant to imitate the local theory from number theory. You know, say indication, like yeah, that one, that formula is sort of understood to be in some sense the geometric counterpart. The geometric counterpart to that is sort of a little bit this Zipf theory. It's called now. So there's this big circle of ideas. The one of the punchlines is that we kind of got around this problem of dealing with this file group stratification and making sure that you really kind of like glue the pieces correctly, compute constant term of Eisenstein. Instead of imitating what happens in number theory and trying to understand those extension classes, we said, here's a trick, do all this Kac-Moody stuff. It comes at a big cost, but it's very similar to other known things. And so that was the way the subject actually developed. Does that answer your question?
Half.
Half, yeah. So maybe I'd say again, like what you should think is it wasn't just about computing weight for coefficients of Eisenstein series. That was sort of the first phase, and that was the easier phase. And then there's the second phase, which is about computing constant terms of Eisenstein series, which is also classically done in number theory. But I would just say the methods to do it in number theory, you run into serious complications if you try to do it in geometry. It's exactly about gluing together Brouhaha strata. So you have to deal with them all together in the flag variety instead of one at a time.
So could you highlight the points of the now where it was important that X was proper and to what extent that hypothesis can be removed?
It was important everywhere that X is proper.
Everywhere?
Yeah.
But G doesn't exist. But G exists are defined when you get that. But without the
So it's just less algebraic than you want it to be?
Well, they're not algebraic stacks. For example, there's like, I mean, all of this run space stuff. It's really using properness and essentially what.
Suppose if I was considering just say the spectral side for like a puncture for supposed to be any.
Yes.
oh, let's answer this question seriously. So the video case. So the video case will understand everything. Let's okay, you know what, let's list the questions because time is we have like until 5 p.m. but let's like it's not infinite time. Okay, we'll answer this right now. Let's list the questions and we'll try this. Oh, you do it?
Yeah, I can do it.
Yeah. But don't erase. Can you read Danish?
Yeah, he needs to get a course, you know.
Yeah.
Okay, so let's say improper curve would be the case. All right, so there were some very cool questions asked before we so what were
You
they?
had a question.
So I wanted to ask about the second cube. There was this Kac-Moody localization, and how much
How much
does
is
it?
this? Okay.
Yeah.
Non-quasi compactness. Okay, so there were some also very cool questions that I deferred to this Q&A. So what were they? Guys, you remember your own questions.
The target of LG in for task or test transmute to temper or task.
Change the cube to temporary. We could do it. Can you ask the question again?
Can you change the targets of LG to be in for temp or task?
So tempered and hospital are both usually adjectives for things that are D-modules. It's sort of understood to be things about Bungie rather than things about local systems. If you want it, yeah. But I can put tempered philosophy.
Describe trick was the area also in the spectral side.
Well, of course, it's most spectrum.
There's an option.
It's lobster. It's O.
Jonathan Hooker, I was wondering why this for random. If it's a particular case of, I don't know, in general construction, where we take local systems and something. Yeah, actually, how it is in maybe some more.
Okay, recorded. So there was some very good questions. I forgot.
Yeah, one other question.
Yeah.
What happens to that constant?
What?
What happens to that
Constant.
Yeah, so the image of the constant shift from the values.
Okay, that we can do.
It was something as well for like, to get some example, like some generating objects of function, give a function and where they go to and put the line on first function.
Perfect. Yes.
Right. For example, the functors or more or less depends on the naives in that case.
Say again.
A well-lens functor kind of uses naives in that case. What if I want to turn on derives in that case as much as I want?
Perfect.
In this
Yeah,
order?
that's it. Yeah. The rest of enhancement. The rest attack for global. Yeah. Ishan event.
Can you say more about why this functor is called Eisenstein? Why it's.
Yeah. What is Gurger?
The answer is Eisenstein studies certain special functions, like some you worked on some kind of.
No, we'll answer systematically. All right. So okay. So any more questions? Yeah.
This one's available for SAT, but I was wondering if you could say a bit more about at what point in the proof of the Grothendieck technique does it become critical that the level is critical?
Yeah. So okay. Perfect. Dima.
I have a meta question. There's a lot of functors, often between dualizable, between self-dual cases.
Yes.
Which means that the functor is given by a curve.
Yeah.
Can you say something interesting about some of those curves?
Let's record it and then see.
And then I know.
Okay.
Yeah, by the way, what about the journals? I mean,
Okay,
this is given by King.
So let's take a picture of this because some of this will have to be delegated to tomorrow. Because we can't possibly answer all of it now. But again, I'm missing some very cool, I think there were very cool questions asked. Yeah, go ahead.
Can you define the row shifts?
Say again?
Can you define the row shifts, the appearance of row shifts?
Well, row shift. Yes, there was a question, it was from Tayu, row shifts. That's what I meant. Row shift. Yes. Yes.
Yeah, time we talk about the geometry of Bungie, the theorem we have.
Yeah. And yet, so there was yet another very cool question. Again,
About lens.
I can't remember. I said let's discuss during the.
It was a nice question, but was it the question about how many modules are seen by the compact use?
No, that has been asked already.
Ah, okay.
Yeah, it's like this. It's right. Let me take a picture of this and then see. Okay. Okay. So let's take turns in the order in which it was received.
No, I wanna cut off some of these quickly. Okay. And I also have priorities here, not in the order in which it was received. Okay, so first I was starting to give a brief answer to why it's called Eisenstein series. Literally, Eisenstein wrote down some kind of special functions. They're called homomorphic Eisenstein series. And what should I say?
It's just pull push. It's not pull push.
Eisenstein.
Don't say it bad about that. But it's pull push.
Yeah, that's what it is, but why it's named after Eisenstein. He wrote down the series, which then later got interpreted kind of much more generality in the context of automorphic forms. That's a different way of understanding automorphic forms.
Looks like you're saying there's something, there's some pull push level if I make it form.
Yes.
Analogous.
So it's like you have GA mod GF, F is a global field. So here you have GA modulo. Oh, it would be embarrassing. BF And here it's GA modulo TF and 8. And so note that if you also mod out the maximum compact, this will be the same as just a TA mod TO mod TF.
TF
NA.
and.
NA. Adelic points of N. So Eisenstein operator, just really what it is, you start with a function here, pull back, pull forward. And again, so if you were to write mod GA, mod GO, or in the function field case, it will be literally 1G over Q, 1 B over Q, 1 T over Q. So what you do, pull back the function, the forward function, the level of sheaves, which is do the same. That's why it has this. Okay, out.
Okay.
Right.
Console sheet.
No.
Yeah.
I'm gonna recover the.
So,
So, okay, I wanna do a guild question next.
the generators will be less for reading.
I'm still gonna say it. Okay, so what demodules on Bungie do we know? So of course, there's all kinds of constructions you can imagine, but the theory prefers 3 of them. So it was written in Kabir's talk. So there's this Poincare sheaves. There's this Katsuni, well, there's this Eisenstein.
And these are analogous to what happens in the function theory. As very Eisenstein, they have brothers in classical theory.
Right, and then there's these Katsuni localized things which do not. A theorem that Joachim will talk about tomorrow is that these two generate. So you get everything already just from these two constructions. And
But the Poincare sheaves is just like the Poincare sheaf, like this one guy, or
It translates there all.
maybe, yeah, maybe you act on it by having
Okay.
it there, so, yeah.
but
And so let's kind of say where everything goes. So there's the direct G type run, there's the split G run. There's this Castellan's like equivalence. This goes to quasi-coevolus G check. This goes to this Poincare series construction to MG. And then here there's quasi-coevolus. This is sort of LG, but
LG.
yes, but no.
LG. Well, if you want Poincare, it's LGL. No, it's left adjoint. A priori.
Yeah, a priori it's less straight.
Opposite direction. Reverse doctor.
Yeah.
No. The arrows.
I'm gonna do it this way. I'll do LG.
But we don't know. You just arrow points right. The arrow points right.
Oh, the arrow, yeah, the arrows point.
Right. That was
That is okay, yes. Oh, let me do LG tool. Allow that.
LGL is fine. Yeah, I would.
But so this is telling you, like, okay, I'm just going to jump ahead and say this. These are equivalent, and this diagram tells you where these Poincare sheaves go under geometric line lines. So it's an answer to the question. So a basic example is you take the vacuum object here, you get this object I like to just call Poincare sheaf. You look at where it goes under the Langlands equivalence, and this is saying it goes to the structure sheaf. That's what it means. That's the hardest theorem in the business, in the sense it's the last one that's proved. It's the subject of tomorrow. But that is what you're supposed to think. So this is, I'll just say as an example, this is saying that O matches and Poincare Shriek under geometric Langlands. Then there's the second one, and yeah,
we raised the doors to say, it's like. That was for the vacuum object, the general, if, like, 8 neck operators and 8 points, you just get the corresponding evaluation correctly one.
exactly.
All the point, literal generator, you don't really care about. What the actual stuff.
For literal generators, yeah, but you need for field value points. And let's just stick to everything's in equivalence. So, okay, let me be more careful because we really good. Connected with this.
Sure.
Okay, so this was proved today, and this is explaining where Eisenstein objects go under the equivalence, saying, well, by induction, you're supposed to somehow know where everything goes under Langlands for the levy, let's say. But maybe you started with an eigensheaf, so it corresponds to some skyscraper sheaf over here. Now you apply Eisenstein series to that object and apply the Langlands functor. And this is telling you that that's the same as take the corresponding object here and do the spectral Eisenstein, this pole push. And so this is expressing the idea that somehow this sort of notion of parabolic induction matches kind of like probing locus G check by a reducible local systems. Good. When there's a then there's this third class, and this is also what was sort of computed over the last couple of days. This KLFG, this maps by this Casimir localization to be a G. This maps to this info nope. Like this we check. This is equivalent to this FLE. This info on non-geometry operators. And this is the spectral Poincare series. And again, this is sort of expressing the idea that, for example, the sheaf of differential operators was matching the structure sheaf on board thing. And global offers push forward to Locus G chat. And the generalization of that sort of assertion. And again, for Beer one can say that similarly, you can take one of the evaluation bundles now in bundle G rather than on Locus G check. You take an evaluation on bundle G, evaluation vector bundle on bundle G, you induce it up to by tensoring the sheaf of differential operators. You can say where that corresponds under Langlands. And the answer is take some file module. Well, the answer is it's some push forward for some operational singularities. That we should proper singularities. So those are the generators. That's kind of what's in some sense what's been going on is kind of slowly explaining. These are the basic calculations of where objects go under geometric Langlands. Did that answer your question? Okay. Oh, and I want to mention just while I have it here, one more, just like this is like I don't think this is like I've never managed to convince myself this is like an important comment, but it's a heuristic I find useful just for like thinking about the subject, which is that there are these three ways of constructing D modules on Bun G, and it's really easy to compare any two of them as long as they're not the same. So when you compare two things that are the same, it's hard. Calculate homes, for example. Yeah. Whenever you compare two things that are the same, it's difficult. So like this diagram is going to be the last one that gets proved in the course of proving geometric Langlands. And that's sort of about computing Whittaker coefficients of Poincare sheaves. You just sort of look. geometric Langlands functor is always about computing Whittaker coefficients, and so this is about computing Whittaker coefficients of Poincare series. But here, this diagram is saying you can compute Whittaker coefficients of Eisenstein series, and this diagram is saying you can compute Whittaker coefficients of Kac-Moody localized things. And then similarly, there's this question earlier about constant term of Eisenstein series. That's comparing Eisenstein with itself. We haven't talked about problems between Kac-Moody localized things with the
Constant term series, finally series, we have computed last lecture at great expense.
Yes, we computed it at great expense. And how did we compute it? We computed it by sort of like plugging in Kac-Moody localized things everywhere. So in some sense, what we were doing is saying like there's this Langlands functor, which is about Whittaker coefficients. We want to see how it interacts with constant terms, and we're sort of plugging in Kac-Moody localized things because they play well with both constant terms and Whittaker coefficients. And that was how we were able to prove the commutative cube that Dennis explained. So just want to say that heuristic while we're here. Okay, so that's the generators. What was that? I don't want to do that.
Let me do the constant sheet.
Let's do the constant sheet later.
Wait, and it's connected here, so that there's right, that's the way you.
Yeah. The surjectivity of Kac-Moody.
It's really installed. Just wait half an hour, you'll see it cancelled.
Okay.
Cool.
Let's do not help tomorrow. Okay, for this.
It's in your talk tomorrow, yes, yes.
Okay.
That's not our will give you also something.
Yeah.
Actually, I had a quick question. So Sam, you kind of explained why for this constant term thing,
Yeah.
why working one cause the fact for the time was.
Yeah.
You basically said we're not supposed to be playing.
No, it takes substantially more work than that.
Okay.
Yeah. Okay. Okay, there's this, I'm gonna cross up this one quickly too. There's this question about why critical level is critical in the birth of opera story. And I would say just the formulation of this birth of operas require the vacuum representation to have many endomorphisms. And that's false off critical level. So there are no endomorphisms of the vacuum besides scalar multiples of the identity off critical level. And at critical level specifically, it has many, many endomorphisms. So Graeber wrote many explicit formulas during his talk, and one of them was for some central elements of the Kac-Moody algebra, specifically at critical level. And scientists who studied the formulas Graeber wrote down a long time ago, like Sugawara is a big name here. They told us that by staring at these formulas away from critical level, you prove exactly that there's no endomorphisms of the vacuum representation, but specifically at the critical level, Graeber's formula gives you a central element. And there's this kind of basic dichotomy in the representation.
Doing something amazing that happens, which I can't recover the full formulation of. What happens is this. So you want to show that the center is large. And it just so happens that if you write down that one operator, everything else spins from there. You kind of have to know that this one Shigawara operator exists and everything else goes.
No, you need to know about Akimoto.
I remember there was something magic even before.
It's like next to another fine related to this, which is that like one side of the over is like we take the vacuum module and we hit the stock issue. Anyway, and in general, like if you're at like level 15 or something, and like the Satake sheet at like highest weight 2, you get basically like the bottom module with highest weight plus 3rd. So basically kind of like it's as you change the level, like the extent to which when you move the highest weight changes. And the critical level is like basically zeros. It's the one time that like you're not imagining it's just kind of coming back to itself over and over.
Yeah, that's very important. Let me say it out loud. Because one, so again, the basic operation we saw many times is convolution of Satake sheets with the vacuum representation. And it just so happens, I'm repeating what Graeber said, like birth of operas is based on the following, that if you convolve the Satake sheet with the vacuum representation, you get the vacuum representation a bunch of times. And that's unique to the critical level. If you're at level 5, and if your if you are at level 5, if you are at level 5,
15.
15, and if you yes, it's additive, right? If you act in vacuum representation, you would get a vial module highest weight 15. And
What do you mean by acting like?
convolve.
Yeah, but like with critical level, you're saying specifically like critical level, yeah.
Yeah, then the level you get something irreducible module weight 15.
Yeah.
Why is it called birth of opers? Actually,
Balance the called birth opers.
because are there opers that can burn?
So again,
Is anything
oh,
born?
so what he
Like-
did, he basically can geometric construction how opers appear. So like this construction gives you geometrically a functor from spec of this Z, the center. To,
Okay, yeah.
So like it really maps from spec Z to opers.
Okay.
Hence
I
you
guess.
you birth opers. Points on spec Z give you opers.
And here we're going
Let me mention one thing in this direction. So there's in general, there's something called the W algebra, which is something called Sokolov vacuum, some level kappa. And there's a general theorem of Fagan and Frenkel that these two are isomorphic for G and kappa and G check in a physically dual level, where it's sort of I'm being a little thing, but a little whatever. So it's kind of like kappa check is 1 over kappa if 0 is the same as critical. Kind of what you're supposed to say. Maybe just take it okay for a second. So they prove this general duality of W algebras, and then they deduce the Fagan-Frenkel isomorphism from this general statement, and which they proved for sort of very generic levels, not at all levels like the critical level, and then they did some little bit of fudging in order to get the assertion at all levels, and they did some difficult representation theory. It's a serious theorem that's been the methods are super important to learn them, but my basic impression is that you can sort of look at this. Okay, when kappa equals 0, this is saying that this WG crit, so this thing which is the Drinfeld-Sokolov reduction of the vacuum representation. So one thing is this really kind of receives a map from the center, and it receives a map isomorphically. It's not so hard to show, at least once you know that the center is big. And then this is telling you that this is the same as this WG check infinity, which happens to be functions on these regular opers. And as far as I understand, kind of the reason this birth of opers is called birth of opers is because you wanted to sort of have two commutative algebras, and like you want to say that they're the same without all this like crazy representation theory stuff that kind of goes into the proof of this theorem. Like it's commutative algebras, we're an algebraic geometer, let's just do it. And I think this birth of opers was designed to give you a map in one direction, it's from here, that you then prove is the Fagan-Frenkel isomorphism posteriori, but at least it kind of tells you like sometimes for a geometric representation theorist or something like where what the geometry of the situation really is. And yeah. At least that's what the name's meant to evoke.
Yeah, it's cool. Actually.
How's the birth of opers formula give you this stuff?
So in Yifei's talk, what he explained is that if you take the spec of the center, then it has some canonical map to this space of opers. And he was explaining what does it mean to give a map from spec of the center into opers. You should give sort of a G bundle on spec of the center times Z, and the G check bundle on spec of Z times the disk, and then you should give a connection on it, and you should give a reduction to the Borel, and you should check some stuff. And that birth of opers, like the main isomorphism, what Yifei explains is that gives you at least a G bundle on stack Z. Then you build off of and do some stuff with. But yeah. And assuming I got the directions right, I think we're closing this thing. Yeah.
Let's move on to the questions.
Yeah, so it's one of the thing that's said about computer, like, okay, the fact that opers are the W algebra of infinity, that's the sense in which like again, like, if that's, it's kind of, this factor kind of looks like the Gaussian slice, so that's it.
And this thing where we write spectral Poincare series, like we think of it as an analog of, like in some sense, what was happening earlier today was that, like, and this these Whittaker coefficients of Casimir localized things were sort of a priori expressed in terms of chiral homology for this algebra, whereas the you should think that kind of the other leg, like, well, the Stringfeld circle of can't say it. The other one was sort of about chiral homology for this guy, and maybe some comparison. At least maybe spiritually that's what's happening.
Yeah.
Okay.
What about the eventual classical limit of your argument?
It's not allowed.
Let's move on with the program.
Discuss, yeah. It's an interesting question that you did not submit in time for hearing. Okay. Do you have a question about how about naive versus derived Satake?
What does Dirac Satake value for property minus number?
Yeah. What is naive Satake value for the properties?
Derived.
What is derived Satake value? But first of all, let me try to say, like, I forget whose question it was. You, okay. What? Okay. There are deep things that you can say about this. I want to say something shallow about it first, which is, why are we always using naive Satake when derived Satake is just right there? And the answer is, we're trying to connect D modules on Bun-G to quasi-coherent sheaves on Lopes G check. And this guy over here is really closely related to this quasi-co-Lopes to this rep G check run. Like, that's the thing that really controls this thing. So we're specifically using naive Satake because that's what gets the job done. So it's kind of in some sense, you could think of it as a hack or something. Dennis probably thinks of it as a hack. I don't know if that's sufficient to answer your question, or if you want a longer answer.
I want a longer answer.
Yeah. So let me say, there's something particular to say.
Yeah. Let me try, and then you say.
Okay, go ahead.
So at first approximation, the answer is. So you can say naive Satake tells you that this D of Bun-G is acted on by quasi-co-Lopes G check. So aka it's like a sheaf of categories on Lopes G check. At first approximation, what naive Satake tells you, what derived Satake tells you, is that this thing descends to a sheaf over Lopes G check Durand. So so it's kind of connection. So like on this thing. So like this category over here descends, like, again, let's just say it's quasi-co-Lopes, like absolutely descends to the Durand space. And so it gives you that kind of structure. Here, this is kind of like slightly off for info versus quasi-co reasons. So the more appropriate statement is that there's an action of what's called like Beraldo's H, which is a capital H to fold. And
Hochschild cochain.
Hochschild cochains. And an action of Hochschild cochains, if you have somehow like a smooth stack, action of Hochschild cochains is exactly descent to the Durand space, but it's something a little bit more sophisticated in the presence of singularities.
Let's recap it out loud. That's exactly it. So the claim is that if you just look, so here a priori the spectral action was the action of quasi-co-Lopes. And the fact that you have derived Satake tells you that this is, so we say a crystal of categories is a sheet of categories of the Durand space. In this case, space is Lopes G check. It's what I call crystal with defects. It's exactly because the difference between info and quasi-co, crystal with defects is actually exactly category in actually this algebra of Hochschild cochains. And so that's what they have. So that's the structure that you have on the left-hand side from the action derived Satake. That's this, nothing else, nothing but that. And so you get for free that this functor from all of this is compatible with these structures, where this structure of crystal with defects on each codes kind of by definition. Well, because it is Lopes. So that's what you get. This is nothing else, nothing but this.
Oh yeah, you have a lot of great questions. One quick
People want a constant sheet. The special will of the people.
Okay, so first. You have one G, then you have the constant G. Now I write this E. And then over here you have equal looks of G check. And here there's this Whittaker coefficient thing. Where you pull back to looks to one end with the twist and you tensor by some exponential and you take cohomology. And if you compute where this goes under this map, this maps to 0. Because the cohomology of the exponential sheaf is the exponential sheaf is equal to 0.
You just say, so the constant sheet was like constant on one, exponential sheet is not constant. I'm just saying
the cohomology is some non-constant sheaves is non-zero famously, but in this case, the cohomology of this non-constant sheaf is 0.
yeah, I don't really care.
Yeah. So this, yeah, so QED is just for no, this is exactly where this funny okay, so what you see is that this okay, what you see from the above is that this is a subtle question and it has to involve int-co specifically rather than quasi-co. And so there's a proposal due to Vincent Lefort, which is very beautiful. And so let me tell you what it is. I'll say it in slightly funny form. So I'm going to say what compactly supported cohomology on Bungie is. So this is the functor which is dual to the constant sheaf. About that. And here's what Vincent says it corresponds to. So we're going to try to do. Okay, the idea, the main idea is the following. So what happened before is if you take, so to say, the constant sheaf on Lopes' G check, that corresponds to the Poincare sheaf on the geometric side. And so we're going to take exactly the same paradigm. We want to say that sort of the constant sheaf here corresponds, or maybe dually, the functor of taking Whittaker, the functor of global sections on Lopes corresponds to Whittaker coefficients over here. It's the dual statement. And what Vincent explains is you should take exactly the same paradigm. So what you want to say is that the constant sheaf or this cohomology is going to correspond to some kind of Whittaker type construction on the dual side. And then the next thing is he tells you what that dual construction is. So I'll say it kind of slightly wrong at first, and then I'm gonna start drawing a diagram and then not done drawing the diagram yet. So before when we did so we had our favorite diagram that we used. So there's this fun end omega, like mapped to button G, and then this maps to A1. And that was what we used. So we just pulled back, tensored with the exponential, and took cohomology. So here, what we're going to do is we're going to take
say it differently. Pull back, push forward to one, tensor with exponential, take a moment.
All right. So here we're trying to imitate the same thing. So we're going to map to a product of copies of Lopes' GA of the curve indexed by the simple roots. So for each simple root, you get or I guess in this case, co-root, you get a map from Lopes' n check to Lopes' GA. Now, which was just sort of like what we used in the Whittaker construction before. Now let's think about how this looks. So Lopsis GA as a stack is like the kind of complex of cohomology of X with a shift by 1 as a stack. So this is something which means I'm taking a little bit non-canonically H1 Durham, a classifying space for H0 Durham, and then a sort of shifted version of H2 Durham. So before, when I dealt with this situation, I was seeing kind of instead kind of some version of like global sections of omega 1 with a shift. This was the stack which was like B H0 and omega 1 times H1 of omega 1. And then I projected onto this sort of one-dimensional factor. Here I'm going to do the same kind of thing. Yes, that means coherent cohomology. This means Durham cohomology. So here I'm going to do, I should have, here it can be a Tal cohomology or Betty cohomology, works in any setup. I'm going to do exactly the same thing, but instead of ignoring this term, I'm going to ignore the first two terms. So this is sort of the term which is sensitive to the genus, and this is one-dimensional in that context. Here, these are, well, no one likes this term. This term is sensitive to the genus, and then what I'm left with is this term. So I'm going to map to a product of omega H2s, H2 Durham, which is the same as the product of omega A1s, which then I can map by a sum map to omega A1. Yeah. So let me just. Hey. The picture slightly better now. So, well, I'm just going to say a slight refinement that I'll need in a second. Okay, any questions about that? Because maybe this is slightly. So omega, it's like omega A1 is stack of K tensor over K of T with K. This is a derived tensor product. So it's a pure algebra on the single generator cohomological degree minus 1.
What's the relationship between that omega and the omega on bottom?
No, that's
Very deep.
So you can actually say it's supposed to be different.
Do it then.
Okay, so now there's this Lopsis n check modular torus. That's what I'm going to use instead. So the torus acts on like just basically because Lopsis B check maps here, I can do this. And if you think about this, the way the sort of equivariance for the sorry. I'm just going to do instead of rows, the row check of GM here. So I'm going to quotient by a single GM acting to the character of row check. And so, yeah. And so now this is going to map instead to an omega A1 mod GM. And now there's a standard calculation, which is that this info called causal duality, this info of A1 is equivalent to modules over polynomial algebra where the cohomological degree of beta is equal to 2. And so it's going to follow that this info of omega A1 mod GM is going to equal graded modules. Where this beta really emphasizes it has cohomological degree 2, so sort of EM degree equal to 1 and plus or minus 1. We'll just call it 1. And so now this category has a canonical functor, the k of beta plus or minus 1 modules. And they're graded, and this is just canonically backed. Basically, if you just think about graded modules over polynomial algebra on a single invertible generator, like that single invertible generator identifies for you all the different weight spaces, and so it's just the same thing as the vector space.
The same as it's exactly both the quasi-product.
It's exactly the quotient by quasi-product. And so now what I can do is I can pull push. To go from intco locus G check to this intco omega A1 mod GM, which goes by the construction we just explained to that. Equal to quotient plus a quote. And that's one sense in which what we did exactly what sense it is to the difference between both. So you can think of this as some spectral counterpart to the Fourier series. Dennis, okay.
Yeah.
If I can editorialize for a second. Okay, as far as I'm okay, there's a precise problem here, which is geometric Langlands is a theorem. Prove that the constant sheaf maps to this object. I mean the object which is dual to everything I just said. As far as I'm aware, no one's done this problem. It seems like a great problem for grad students. It's very close to many things that are known, and it should be a solvable problem. But it's a little bit different from the compatibilities that we've discussed so far, in the sense that like the main thing that kind of keeps happening is you really kind of reduce all of your calculations to this LG course, which is going to quasi-co, and like I explained up here, that doesn't work here. So you need a more refined analysis of Eisenstein series to do this.
So yeah, you need a break between this and Lind's talk. But I haven't answered the first question, in which you already told. You see, in Robert's question about improper VOC. Improper VOC. For the tools. Yes.
What sense exactly is between the constant sheaf? Like you're using the necklace?
Yeah. Yeah. That's easy. Okay, so
This topic is like, look, you're prepared to local system. Something you look at like system modalities with that.
okay, so in the case of I should say in the case of P1, Bunsen proved this. And we did that by causal validate equivariant cosine. It's very, very part of what we were saying is that this is very similar to Ginsburg's favorite point of view on stuff.
Effectively, they just from
Yeah. The P1 case.
general case.
There's not enough people reading basis.
Yeah. There's a company called Finkelberg basically looked at this. But they didn't talk about P1, that's not what was no group. Right, so that their shot was absolutely P1. Great.
Like go to higher use. Not system.
It's a problem for graduate students.
Right.
Okay, so in the case of GM, okay, so what happens? So Robert asked, what if we consider everything for a non-proper curve? So I'm going to take 1 GM on x minus x. So kind of like
We can just do it. We can.
X minus 11 points. Okay, so this is like fun GN of X, but it can quotients by the points. Well, yeah, maybe it's a couple points, and I'm gonna quotient by like all of these O of Xi's, and so it kind of quickly becomes to me a chaotic mess. So like first I quotient by O of X, and that eats up the Z factor, and then I quotient by O of Y, which is like taking the Jacobian and quotient by O of X minus Y. And so it's like some kind of Billian variety mod Z squared, and if you did this for SL2 instead, then it's a stack with no geometry, it's just a classifying stack. So this thing, you feel quickly, it's not the right thing to look at.
But wait a second, we can answer, we can say what it is in terms of.
I will.
Okay.
Okay, then there's this other thing here, which is that you can take what's this GM of X minus 10 points. Actually, let me write X so function first. This is something great. I mean, some in scheme, it's not in stack, in algebraic stack. But in the Storam world, what you're supposed to imagine is you take some kind of like vector bundle from connection, and there's some issues with order of pole of connection, but it's something. And you can ask about quasi-coherent G from this space, and what you can check is that this is the same as category of B modules not here, but on the space of line bundles on X with a trivialization around the function. So in some sense, this is kind of like impact is supported on this side. And that's the kind of for general. So this is just a true statement. If you want, you can. Okay, this side has an action of the loop group for GM. You can quotient, and you'll end up with that space in the core. It's fun GM on the function curve. You can quotient by the corresponding. You can say what that action corresponds to over here. Quotient by it. Use them to the statement of the other type as well. But you're gonna have to. It's like in Poincare duality for something non-compact. You like if you want some duality statements, you need to have compactness for this type of the other. I assume you get local systems on Xserve with the trivialization when the function goes to infinity.
What?
I don't have the exercise in mind.
For what?
If you quotient by the LGN action over here.
But it's D modules, so you don't really need to quotient by the infinitesimal stuff.
Yeah.
So basically you do really have just lattice, what you started. Yes, here you're going to have local systems trivialized over formal history, you have like a GM extension.
Yeah, exactly. So it will be compactly supported local systems, like you said. Yeah. Same as local systems on X, trivialized all of this. Amazing. So these are equivalent, and there's a sort of conjecture which isn't which says that if you take this category of D modules on G with a full level structure around some points, again sort of compactly supported bundles. And so this is going to have an action of this loop group, and you can take this Whittaker star or Whittaker sheaf or whatever you want to call it. And this should be equivalent to quasi-coherent sheaves on the space of G-check local system on this composite. And so that's a generalization that people expect. This Whittaker construction is vacuous in the case of a torus. So this is sort of the kind of thing.
Vacuum does nothing.
Yes.
Identity.
And is there a further conjecture that removes width on one side and appropriately renormalizes the right hand side?
Yeah. So there's somewhat. So there's the following assertion. So there's supposed to be this local geometric plane lens. Okay, let me take more space. Okay. So the dream is that there's supposed to be some kind of local geometric lens equivalence, which takes the following guys as input. So you take categories with an action of LG, And this should be equivalent to some kind of 2 code nil. There's a thing just going to be imagined by Dima. And that Stefanish has done a lot of work about. And this base of local systems for check on the country disk. Yeah, Jerome local systems. A sort of like working person's version of this has been announced by Kabir and David Yang. And Yasha, Varshavsky. And so this is local geometric lens. And let me just, so it's kind of like some kind of category here goes to some kind of dual category over on this side. And maybe one of the basic compatibilities here is that if you take this Whittaker functor down to just to extract some category with no LG action, this should kind of correspond to taking global sections on this locus. Let me emphasize on the function disk with coefficients and corresponding dual things. So that's kind of why Whittaker occurs here. But the expectation, the sort of what the general pattern in Langland's theory is that, like, if you want to do some kind of like global stuff, then at each prime of ramification, you need to understand local Langlands, at least up to that order of ramification. So what I say will be conditional on local Langlands, and it should be, but the expectation is that basically this deviated bungee with the level structure is going to correspond to some kind of encode nil locus check curve. This guy is kind of smooth, so nil doesn't really make sense.
It
But
does.
and it does make sense in this universe.
Okay.
Exactly. And so that's the right setup.
Sorry, this is just for, there was a very fun question of, so then, how do I apply with mumbo jumbo, just remove weight from it?
Right.
To remove what?
If you want to remove width from this thing, what do?
You do this.
This is what I would say.
You just tell them what this implies to be on. That's what the thing with the flag.
No, let's not do that right now.
Right.
Yeah.
You can extract from this an actual that you can remove the width the way that wanted.
Yeah.
It's kind of.
Kind of complicated and specific to GLI.
Well,
Right, guys, let's have a break. Because we have another hour.